Good afternoon, Physics 20. Welcome to our last video of the unit. So, ladies and gentlemen, if you are in class, or we are all in class in the building of St. Joe's, you got a unit test coming up. It will include everything we have done in kinematics so far. So, once again, I have no idea what's happening with COVID, so we'll figure out the details of how the test is going to work when we get to school. If we're at home, then you have no test, but you have an assignment due. Either way, you have an assignment due after this. So if you are slacking on getting your assignment done, get her done. Okay, so ladies and gentlemen, today we're going to be looking at relative motion. Now this is cool. I really like this particular topic because it's so practical. This is the type of thing that airplane pilots need to keep in mind. And back in the day, before they programmed computers to do it for them, they would have to do this math when they're flying in a wind. Pilots of a boat or captains of a boat would have to do this type of math in order to get across, to just deal with ocean currents, to deal with flowing rivers, what have you. There's the whole concept of relative motion. It's where you have problems that are going to involve scenarios where not only an object is moving, but so is the medium the object is in. Now, the medium is the stuff around you, right? So that would be the air or the water. So your examples are a person swimming across a river, which I don't really recommend unless you're a very, very good swimmer. But yeah, don't swim in fast rivers. Or like a boat in a river, a plane being blown around in the wind. And you can actually see this. It's pretty cool. When you watch airplanes taking off or landing in high winds, you'll notice that the airplane will be coming in sideways, and it's coming in landing like this, and then boom, and then lands. Like it's really, really cool to watch. So yeah, it's definitely very practical thing that gets used. Okay. So when we're going to be solving relative motion problems, ladies and gentlemen, we're going to be dealing with more than one type of measurement. So time, displacement, and velocity, they're all going to be given. So we're going to have to keep track of where everything is. So keep in mind the following pieces. Number one, you absolutely can use trig and Pythagorean Theorem. However, these guys only work if the sides of the triangle that you're working with have all the same units. So you can't use velocity and displacement in your triangle. It doesn't work. So if you're trying to use Pythagorean Theorem or you're trying to use trig, you must keep the units the same. Okay? Another thing to keep in mind is time on all sides of the triangle is going to be the same, okay? We're just breaking the problem into individual chunks to solve, but each scenario is all occurring simultaneously. So time is going to be the same on all sides of your triangle, okay? All right. So, ladies and gentlemen, we've got a series of problems here involving a river, and we are going to solve them. That's really the best way to learn this is dive in. Dive in, we're dealing with river problems. Yeah. Okay. So, ladies and gentlemen, a boat with a speed in still water of 5 meters per second is heading west across a river. The river current is 2.5 meters per second south. Okay. Now, if the current is going south, that means you're going to need to draw your river going north-south. Now, trust me, guys, this is going to be a lot easier if you draw this. You're not going to be able to do this if you draw it. So, the boat that we're dealing with, if the water was still, it would go across like this. Okay? All right? Well, however, the current of this river is going south, at 2.5 meters per second. Okay? That means the route that the boat is actually traveling is here. It is being pushed this way. So what is the velocity of the boat relative to the shore? Well, velocity, that's a vector, so I want direction. Relative to the shore, what that is going to tell you is that we are going to be wanting your angle to be touching the shoreline. Okay? So we're going to come back to that when we start looking at our theta. All right. So, ladies and gentlemen, let us begin. So we are trying to find the velocity relative to the shore. Remember our rules here. We absolutely can use Pythagorean Theorem, and we can absolutely use trig, so long as our units are the same. Well, look at this. Meters per second, meters per second. Good. We can do this. So to get my resultant here, I'm going to use Pythagorean's theorem. So C is going to equal a squared plus b squared square root. And I'm going to put my values in. So 5 squared plus 2.5 squared. Remember, the squaring happens first, then the adding, and then you square root the lot. Okay? Once you plug that into your lovely calculator, you are going to wind up with C, which is going to equal your resultant velocity. And that is going to equal our 5.59 ... meters per second. Okay. Well, I said vector, ladies and gentlemen. So we have a couple of options because remember, the theta that I want is blue theta. I want blue theta because I said relative to the shore. That means this is your shore. So I want a theta that is going to start here and go that way. Okay? All right. So we've got several different options. And in order how to pursue this, I'm going to go this way. I'm going to calculate red theta first, and then I'm going to subtract red theta from 90, and that will give me blue theta because that is a 90-degree angle. Okay? All right, so that's the route I'm going to go. There are other ways you can go, but that's what I personally would find the easiest. So I'm going to first calculate my red theta. So my red theta is equal to the tan of my red theta because I have opposite and adjacent. Remember, I do have hypotenuse, but don't use the hypotenuse because it's had math down on it already. Okay, we don't want to have a multiplication of errors. So the tan theta is going to be our 2.5 over 5. Okay, and I'm trying to find theta, so I want tan negative 1 of 2.5 over 5. So I'm going to grab my calculator, which is underneath my formula sheet, and I'm going to go second tan 2.5 over 5. And that is going to give me the lovely angle for my red theta of 26.56 ... degrees. Now remember, that's red theta. Blue theta is what I am looking for. Okay, so blue theta is going to equal 90 minus that answer. So 90 minus second answer, and that is going to give me, so 90 minus 26.56 ... That is going to give me the lovely value of 63.4349 ... degrees. All right. So, ladies and gentlemen, I am now going to combine these numbers together, and I am going to get my velocity of, now I want 2 sig digs here. See, all my values of 2 sig digs. So we've got 5.6 meters per second at 63 degrees relative to the shore. Okay. Now, because I said relative to the shore is what I want, that is how you can communicate your answer, because that's what you've given me. Okay. So, ladies and gentlemen, the big point of this particular question is to show you your, how when you have all the units on the same side, you can use Pythagorean Theorem and trig so long as your units are the same. All right, so we're going to look at the next piece. Okay, we're going to be adding some data, which just means I'm going to have to redraw this here. Okay, so normally in class, I would just draw this once and just build on it for all these questions, but if you're watching this, you're not in class necessarily, or I'm not in class, or heaven knows what's going on, or you're using this to study or whatever. Anyways, okay, so that was 5 meters per second. This was 2.5 meters per second. Dot, 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 dot. And this guy was, of course, can't remember our final answer now, 5.6 meters per second. And this theta was 26.5 degrees. Okay. So we have that data available to us. Remember, try to avoid, if you can, using these two numbers, simply because you'll have multiplication of error. Now we're going to add some new data. If the river is 2,395 meters wide, so that means all the way across, that's a 9. Okay. How long does it take the boat to go across the river? Well, we are trying to find time here. Because we're trying to find time, and we're dealing with uniform motion, what's a good way to go? V equals d over t. We have velocities and we have a distance. So we absolutely have a distance of 2,395 meters. Remember that time is the same on all sides of the triangle. When you're breaking this object's motion down into its component parts, but time's the same on all sides. So, technically speaking, I could use any side of the triangle I want, so long as I have enough data on that side. Well, on my triangle, notice from here to here, this is going across the river. Okay, I'm going to change this line to, well, I've used blue. I'll change this line to blue. Notice that this guy is going across like that. And this here is that space. I can use v equals d over t so long as I'm working on the same side of the triangle. Okay, so I can use v equals d over t here. Okay, and it will get me time, which will be the same on all sides of that triangle. Whoops, have to be consistent in my colors. All right, so I am going to use the speed of 5 meters per second because I'm going to be using this guy here. All right, okay, so ladies and gentlemen, v equals d over t. Trying to find time, so time equals d over v. And I'm going to put in 2,395, divide that by 5, and I'm going to get a lovely time of 475 seconds. Well, 5.0 are your smallest sig digs, ladies and gentlemen, because that is the value given to you for that speed of the boat. So what that means is I have to round my answer to 2 sig digs. This is 3 numbers, so I'm going to have to put this in scientific notation. 1, 2 sig digs. That means this 5 will round that 7 up to an 8. 1, 2. Oopsie, I forgot to write down my times 10 to the power of. Okay. There you go, ladies and gentlemen. Okay. So the math with these calculations aren't hard. It's just fighting your way through the theory to figure out what signs you need, what data you need, what data you have. That's the hard part of these questions. Okie doke. How far downstream is the boat when it reaches the other side of the river? So for this one, I'm not going to redraw this diagram here, but I'm going to switch my color to this pink. So how far downstream? You have been asked to calculate distance on this pink side of the triangle that I'm drawing here. That is what you've been asked to calculate, is the distance there. Okay. So there's a couple of different ways that you can go with this. You absolutely can use time if you like. You absolutely go for it. You could use your angle, and you could use the distance that you have for this side, and you can use trig. Either way, it's just fine. You're going to get pretty much the same answer. There's going to be a little bit more error in this one, but it'll be close enough for our purposes. So I'm going to choose V equals D over T because it's easier to put in my calculator. But I can do that because time is the same on all sides of the triangle. So I can use this time here, the 475 seconds, and use that with this 25 meters per second here and get my how far downstream we are. Okay, so that's what we got to use. All right. So, oopsie, can't do the calculations in pink. So, V equals D over T. And remember, the speed in which we're using is the 2.5 meters per second. Time, we are going to have to use the time from the previous question of 475 seconds. And honestly, there's no way you can go about this without having a value that has had math done on it for the second step for question C here. So using time or your angle, you're going to have some type of error. So you got to do it. So now we're trying to find how far downstream. So velocity times time is going to equal the distance. And so our 475 seconds multiplied by 2.5 meters per second. And once you plonk those into your calculator, you're going to get 1,200 meters. How many sig digs do I want? 2. So that means you are going to have to put this into scientific notation. So 1.2 times 10 to the power of 3 meters. I said how far, so that means scalar, so I do not want direction. All right. Okay. For those of you who want to use trig, we will do that now. The time rounding is done, you should have the same answer. I'm going to switch and do that in blue. So we are going to need to be using the same units. Okay, you have to make sure your units are the same. That's the tricky part with this. So we've asked for how far downstream. So that means I'm going to redraw my triangle here. I'll do that down here. So if you want to use the trig method, you're going to use the blue ink. So my triangle is going to be the 2,395 meters. Okay. You have been asked to calculate this distance here. Okay. So this is our triangle. You calculated this 26 point, oh, come on, computer. It's being a bum. Yeah, 26.5 degrees. Now remember, you can't use just 26.5 degrees. You have to use your unrounded number. Okay, and you can use that to find this value here, this distance on this side. Okay, displacement, so it doesn't need the arrow over top. So ladies and gentlemen, if we use this with trig, our units are going to be the same. Okay, so we have our angle opposite and adjacent, and we have theta. So tan of theta is equal to opposite over adjacent. We have adjacent and we're trying to find the opposite. So I am going to multiply by my adjacent. Okay. Now remember, ladies and gentlemen, you can't use just 26.5. So 26.565 ... You got to use the whole shebang here. It has to be 26.6 if you're writing it down. Anyway, for a final answer. So you got this. You're going to multiply both sides by the adjacent, okay, which is, we'll write the numbers down. So the opposite is the distance, okay, on this side. And then the adjacent is 2,395. Multiply both sides by that value, so 2,395 times your tan of 26.565 ... will give you your distance. Okay, so I'm going to use my calculator because I didn't do this earlier. So I'm going to take my 2,395. Then I'm going to multiply that by the tangent, scroll up, get that full number that you calculated earlier, hit enter. Okay, so I get this value. Okay, it's a little bit different. It's slightly off, but I want 2 sig digs. So because I need 2 significant digits, I'm going to have to do some rounding. 2 sig digs. I'm going to come to these guys. I am going to then, this is going to force me to round this number here. So I get 1.2 times 10 to the power of 3 meters. All right. So you can go either way with this question. I find the V equals D over T easier. But some people find the trig easier. That's why I showed you guys both ways to solve this. So that way you can pick which method you want to use depending on if the problem allows for it. Cool, guys? Go Bates. All right. So, ladies and gentlemen, now this is a tricky one. This one we need to redraw our triangle here. Okay. This is where you're going to see those airplanes coming in for a landing, flying at an angle. I'm going to see if I can find a YouTube video for you guys to go with it. And I will put this video in the Google Classroom page where you found this video. It should be there. If I can find one. I'm sure I'll be able to. All right. So, what direction, so that means I want an angle, does the boat need to head so that when it reaches the opposite shore, it is directly west from the starting point? Okay, so I'm going to draw this again. So here's my river. Okay, now the boat is dealing with a current that is going south, so 2.5 meters per second going south. Well, the boat's resultant, its final vector, it wants to be here. It wants to be directly west of where it started. Okay, so that's the resultant it wants. So where's it going to have to go? Well, the boat is going to have to point its nose upstream. So you're going to, if you want to go straight across a river that's going south, you got to point yourself upstream. And when you're doing that, it's going to look kind of silly. Your nose is going to be pointing up the river, okay? So you're trying to go straight, but you're going to be canted sideways, and you're going to be going like this, okay? So that's why airplanes will fly sideways into the wind, as because they're fighting the wind. All right. So what direction does the boat need to go? That means I want this theta. Now, lesson settle hand, I've given you a question on this on your assignment for sure. So, well, if the boat is pointing its nose this way, remember the boat can go 5 meters per second. All right. Okay. So we now, can we calculate our theta? Well, of course we can. We have all sorts of other data. We've got distances and all sorts of things, how far it is downstream. But those aren't as helpful to us because, well, we have the speed of the river here and we have how fast the boat is going. You can use trig and you can use Pythagorean theorem if the units are the same. So this is another case of that. So, ladies and gentlemen, let us do some trig. So I'm trying to find theta, and I have my opposite, I have my hypotenuse. That means I am going to use sine. Sine of theta is equal to opposite over hypotenuse. I'm trying to find theta. So I am going to sine -1 on both sides. My opposite is 2.5. My hypotenuse is 5. And that's going to give me theta. Okay, so your theta, once you do that, gives you 30 degrees. Now, I did not specifically say relative to the shore. This 30 happens to be in appropriate sig digs already. So because I didn't say what reference I wanted, pick a reference. Well, here's the west line. And in order to reach there, we have to go north. So it's north of the west line. So 30 degrees north of west. Okay? Okay. So, ladies and gentlemen, you can still refer to shoreline if you want. You can just go 90 degrees minus 30 is going to give you 60. And so you're welcome to say that theta would equal, so that would be this theta there. So it would be 60 degrees relative to shore. So both mean the same thing. However, you just need to communicate your reference point. And if it's a multiple choice question, then just check and see where your theta is. All right, guys. So here are your practice problems. Take a crack at some of these and see how you do. If you have any questions, make sure you come and see me. You now should be able to finish completely your kinematics chapter 2 assignment. And if we are in class, then we are going to be having a unit test shortly hereafter. So make sure you get that assignment done. Trust me, guys. I've been teaching long enough. This is I'm starting my 10th year of teaching now. And people who do their assignments before the test do better on the test than people who don't do their assignment before the test. I even done the math on this. It's statistically relevant. It works out that way. So, ladies and gentlemen, get your assignment done. Get it handed in before the test. If we're in class and have a test. This is the end of the unit. Next unit, dynamics. All right, so have a good rest of your day. No fires, injuries, or explosions. See you next time.